Good day and welcome back to our discussion on double integrals. This will be the third and final installment on iterated integrals, which we've discussed in the previous two videos, where we have introduced the associated properties and we've investigated several examples. We will finish the discussion with just one more additional example. In this case, we're asked to evaluate a double integral over the rectangle 0, 1 times 0, 1 of the given function. So just to remind us, this first interval is telling us where we find the x values. The second interval is telling us where we find the y values. And before diving directly into this example, at least in terms of work, it's worth taking a step back and asking ourselves, does this integrand function separate into a function of only x times a function of only y? And in this case, I'm just going to simply write does not separate. And since it does not separate, we can't break it up into two single integrals. But instead, remember, we do have this ability to choose which variable we integrate with respect to first when we are integrating over a rectangle. And up to now, all of our discussion has been integrating over rectangles, but in our next section, that's going to quickly change. So we have this basic template, and what we need to do is fill in this order of integration. What do we want to be this first or inside integral? Looking at our integrand function, the observation I would make, and this is something that the more we practice, the more we build up our experience, hopefully the quicker and more efficiently we'll make these observations, is if I think of that 1 plus xy as potentially being a u, which variable would I have to differentiate with respect to make that x in the numerator become my du? And if you said y, I agree. So if we put y on the inside and x on the outside, we can start off by using a substitution. And our substitution would be u is 1 plus xy, and du is exactly what we see, x dy. So I'll extend that over. And we now have 0 to 1 with respect to x on the outside. That is unchanged. On the inside, we have an integral that we're going to express solely in terms of u. 1 over u du, but those limits of integration need to be determined. So we're thinking lower limit of integration is y equals 0, which implies u is equal to 1 plus x times 0, which is 1. And for the upper limit of integration, when y is 1, u is equal to 1 plus x times 1. So that would be 1 plus x. And remember, it is perfectly reasonable to have a variable as your inside limit of integration, as long as that variable is the outside variable. And additionally, those outside limits of integration must be numbers. So now we're in an ideal scenario. Since we've changed those limits of integration, we simply evaluate this definite integral with respect to u. So natural log absolute value u, we're evaluating from 1 to 1 plus x. So we replace the u with a 1 plus x, minus sign replace the u with a 1. And note, natural log 1 is a common value. It's equal to 0. So we'll just cross that term off. And what remains is the antiderivative of a natural log. And when we encounter this, what technique of integration would you recommend? And if you said integration by parts, I agree. So let me rewrite this. We have the integral from 0 to 1, natural log 1 plus x dx. And let me remind you with integration by parts. Integration by parts works extremely well when you have certain types of functions you would like to integrate. It works well for a polynomial times an exponential. Note that could be x squared, it could be e to the 2x instead of an e to the 1x. It works really well when you have a polynomial times a trig function like cosine or sine. And it also works really well for inverse type functions. And inverse functions for us would include things like natural logs, inverse tangents, but more specific to this example would be the natural logs. And what integration by parts tells us is the integral of u dv is uv minus the integral of v du. And the idea is that the integration by parts doesn't completely solve the integral for us, but it instead expresses it in terms of a simpler, easier to evaluate integral. And in the course materials on Canvas, you can find an integration by parts resource. So in terms of the problem that we are dealing with, I see a single function. And when I'm applying integration by parts, I do want to be careful how I choose my u and the dv. You know, at a minimum, dv, whatever we choose it to be, has to be something we can integrate, because we want to undo the dv to find v, and ideally du would become simpler when you differentiate it. Now in this case, I'm going to write something down and then I'm going to erase it. If I was to set the natural log of 1 plus x to be my dv, that wouldn't make sense, because if I knew how to integrate the natural log, I wouldn't need the integration by parts. And we integrate to go from dv to v. So let's get this out of the way. It's also maybe worth noting that because we're ranging from 0 to 1, we actually don't need absolute values. So if we let u be the natural log of 1 plus x, we also need a function for dv. And note it's this 1 hiding in there. So we could let dv be 1 dx, so that dv is, the antiderivative of dv is x, and du would be 1 over 1 plus x. And integration by parts tells us uv, so that would be x ln of 1 plus x from 0 to 1 minus the integral of v du. So in this case, that would be x over 1 plus x. And this is probably a good spot to remind us that it's really important to use good notation. Our work should roughly look like what we see on the screen. You start off with the original double integral, you line things up vertically, we read math vertically, and at each step you're showing equal signs, limits of integrations, differentials, the dy, dx's, du's. If you need a technique of integration, you just put that work to the side so that we have a nice vertical alignment of work. And also note that the good notation is more important than ever just because of the length and difficulty associated with some of these problems. They can be involved. So working from left to right, we substitute in x equals 1, so that would be 1 ln of 2 minus sign, we substitute in 0. Then what remains is one more integral. And as long as we can take care of this integral, we will be good to go. And there are multiple ways to go about this. For example, you could do a substitution. Maybe we would say let w be 1 plus x, and you could evaluate it that way. Alternatively, I'm going to simplify this algebraically in a somewhat subtle way, but I have the following motivation. What number would be nice to add to this x in the numerator? And if you're thinking a plus 1 would be nice, I agree. If I could somehow make that 1 plus x, well, 1 plus x over 1 plus x is 1, and that's a very easy antiderivative. But I can't just simply add 1 for free, but I could add 1 and subtract 1. That's just a net 0. And the reason we would do that is we can now break this up into two fractions. You have the 1 plus x over 1 plus x, which is 1, and then you're subtracting away from that 1 over 1 plus x. So we have natural log of 2 minus, and if we anti-differentiate term by term, the antiderivative of 1 is x, and the antiderivative of 1 over 1 plus x is the natural log of 1 plus x. And note once again, we've already indicated that on this interval from 0 to 1, the natural log of the 1 plus x going into the natural log is positive. So we don't technically need the absolute value, but just for good practice, to make sure we're all on the same page, I'm going to go ahead and change those. And we're almost there. Replace each x with a 1, minus sign, replace it with a 0. So 1 minus natural log of 2 minus 0 minus natural log of 1. And we better take this one more step. Remember, natural log of 1 is 0. Distributing this minus sign through, we end up with 2 natural logs of 2 minus 1. And as I've mentioned, hopefully this helps to illustrate that the problems we encounter can certainly be involved, just like we've seen with many examples of integration back when we were in Calculus 2 and even Calculus 1. So these do require a bit of patience, also a bit of perseverance. Don't be afraid to try one technique of integration to see what happens. And as usual, there are plenty of suggested problems that come from section 15.1. I highly encourage you to work through examples. If you have questions, reach out to me, send an email, stop by virtual office hours. But this finishes our discussion for the current topic. In our next section, we will start investigating how we can integrate over regions that are not rectangles. So stay tuned and take care.